Welcome to this video about the semi-discrete form of the wave equation in terms of the finite element context. We now have the following system. We would like to find the acoustic pressure, the discrete acoustic pressure, such that it holds for all discrete test functions. The PD is satisfied, and also the boundary conditions, which are more or less in the function spaces defined there. So to sum up, we would like to find the acoustic pressure based on this equation. And this equation is now a semi-discrete form. Why it's called semi-discrete? Because the space is already discrete and the time derivative is here still continuous, and this is why we call it semi-discrete form. We can rewrite, when inserting the nodal finite element ansatz here into the functions, we can then derive a system of equation according to the unknowns. And the system of equations looks like this: that we have an algebraic system which is a vector matrix, vector multiplication in each term, and so because it should hold for all functions, test functions, so we obtain a system of equation which we more or less have a non-trivial solution for the test function. We would like to search for a non-trivial solution for the test function, so that the system is satisfied for the acoustic pressure. And this is how it works. We have more or less this algebraic system, and this is now the system we would like to solve. In order to solve the system and how to obtain the matrices itself, we would need to assemble the matrices. The matrices or the algebraic system is then assembled, and is mostly programming work. It's very similar to accounting. More or less, we would need some relation tables and how we insert certain contributions of the integral into the matrix itself. And this is what we mean by assembling the system of matrices. Additionally, we already talked about the Neumann boundary condition and the Dirichlet boundary condition. The Neumann boundary condition is naturally integrated into the finite element algorithm, but there is a special topic for the Dirichlet boundary condition. This is not so easy. Either there are two possibilities to integrate the Dirichlet boundary condition, which are typically used. The one is that we use elimination of the equations. It's more or less a programming work, or we use the application of the null space, which is a mathematically equivalent approach to the elimination of the equations, and this is how we can incorporate the Dirichlet boundary conditions. Thank you for watching this video about the semi-discrete form and how to get actually to the algebraic system of equations. As we use a standard nodal finite element results in the semi-discrete Galerkin formulation, we have a system of all ODEs, ordinary differential equations in time, and we can represent it in this form, that we have a mass type matrix, then the second time derivative of the unknown plus a sort of stiffness matrix, and the unknown is equal to some forcing. Here in the solution, unknown vectors simply collected all the pressure at the nodal coordinates. The mass matrix is more or less assembled as a product of the basis functions, and the stiffness matrix is more or less assembled from the gradients of the inner product of the gradients of the basis functions. And the forcing vector is simply the product or the projection of the force, the local density force on the basis function. And this is what the forcing vector gives us. So in this sense, we can calculate very efficiently all these contributions and then evaluate the semi-discrete form and come to the solution variable. Thank you for watching this video about the solution technique on the semi-discrete form.